Welcome back. In this video, I'm going to explain how a 95% margin of error leads to a 95% confidence interval. And to explain that to you, I'm going to share an example involving an imaginary city. So let's imagine that there's this city, and someone comes along and wants to know what the mean age of the city equals. And somehow this person knows that the standard deviation of the ages in this city is 12. But the person doesn't know what the mean age of the city equals, and the person would like to know what it equals. And let's also imagine that for some reason, this person doesn't have enough time or resources to survey all members of the city and ask them for all of their ages. So what the person does is the person decides to estimate the mean age of the city using a random sample. So this person takes a random sample of 36 people, records their 36 ages, and calculates the mean age of the sample of 36. And let's just hypothetically imagine that these are the 36 ages that this person records in his or her survey. So, like I said, this person does a survey with a random sample and asks 36 people who live in the city for their ages and calculates the mean of the sample by adding the 36 ages and dividing by 36. And the sample mean comes out to 37. You could check that if you like. You could check my work and add up these 36 numbers and divide by 36, and you would see that I got 37 when it's rounded to a whole number. So this 37 is what this person calculated, and this is the person's estimate of what the mean age of the entire city equals. So whenever you calculate the mean of a sample, it's an estimate or a best guess of what the mean of all population members equals. So the mean age of the entire city is unlikely to be exactly 37, but it's likely to be close to 37. So now let's move ahead and let's imagine that the person calculates the 95% margin of error. So what this person does is the person multiplies 1.96 by the population standard deviation of 12 over the square root of the sample size of 36. And the square root of 36 is 6. And 12 divided by 6 is 2. And then 1.96 times 2 is about 4. I rounded it to a whole number just so my visuals would come out a little bit nicer. And I did the same thing with the sample mean of 37, just to make my visuals that are coming up look a little bit nicer. And now let's think about what this 95% margin of error is telling us. Well, we can make a diagram to help visually display it. So what it's telling us is that when this person took this random sample of 36 and recorded their 36 ages and calculated the sample mean of 36, the person had a 0.95 probability or a 95% chance of getting a sample mean somewhere between 4 below and 4 above the population mean, between these 2 points. In other words, the person had a 0.95 probability of making it somewhere inside this window of accuracy between 4 below and 4 above the population mean. The person had a small chance, a 0.025 probability of getting a sample mean more than 4 below the population mean. And also the person had a 0.025 probability or a 2.5% chance of getting a sample mean more than 4 above the population mean. But those two outcomes are both unlikely. And if you add these three numbers, 0.025, 0.95, and 0.025, you'll see that they add up to 1. And I want to quickly explain why they add up to 1. That's because when this person takes a random sample and calculates a sample mean, there is a 1.0 probability or 100% chance of the sample mean falling somewhere on the number line, because the sample mean has to come out to some number. So if you think about it, it makes sense that these three numbers add up to 1, because 1.0 is the highest that a probability can be, and it just basically means that there's a 100% chance of the sample mean coming out somewhere to some number. So now let's move ahead and let's quickly recap what this 95% margin of error is telling us. So it's telling us that the sample mean had a 0.95 probability of falling somewhere between 4 below and 4 above the population mean. And we can translate that into a similar statement. So what we can now say down here is that we're 95% confident that the sample mean came out somewhere between 4 below and 4 above the population mean. That's because if we know that this had a 0.95 probability of happening, or a 95% chance of happening, we're 95% confident that it did happen. So probability and confidence go hand in hand. So in other words, since the sample mean had a 0.95 probability of coming out somewhere between these 2 points, so we're now 95% confident that that did happen. So now we can actually take this and turn it into another statement down here and say we're 95% confident that the population mean is between these 2 points right here. And these two statements are actually saying the exact same thing. And I'll quickly explain why. So I'll break down what this is showing down here. So let's imagine for a moment that the sample mean of 37 came out at this point right here, exactly 4 above the population mean. So let's imagine for a moment that this person's sample mean actually did come out at this boundary point, and the person did get a sample mean 4 above the population mean. Well, we know that the sample mean is 37. So if this sample mean of 37 is 4 above the population mean, then that would mean that the population mean is down here, 4 to the left, and the population mean equals this number down here, which is 33. So basically, if the sample mean of 37 came out here and it is 4 above the population mean, then the population mean would have to be 33, because this would be 33 at the center, and you go 4 up, and that would be 37. And now let's imagine for a moment that the sample mean came out down here, and it's actually 4 below the population mean. Well, if that happened, then the population mean would have to be 41, because if we know that the sample mean is 37, then if you go up here to the right, you get to 41. So basically, what I'm saying is, if the population mean is 41, then the sample mean of 37 is 4 below the population mean, and that would put the sample mean out here at 4 below. And if the population mean is 33, then that would mean that the sample mean is 4 above the population mean in this direction, and that would put the sample mean of 37 out here, at this point out here. So basically, if we're saying that we're 95% confident that the sample mean is somewhere between 4 below and 4 above the population mean, and we know that the sample mean is 37, then that's really just another way of saying that we're 95% confident that the population mean is somewhere between 33 and 41. So yeah, if we're 95% confident that the sample mean is somewhere between 4 below and 4 above the population mean, then we're just 95% confident that the population mean is somewhere between 33 and 41. That's saying the exact same thing. So what we've done is we've actually taken our 95% margin of error, and we've actually turned it into a conclusion or an inference about the population mean. So when this person who collected this data reaches his or her conclusion, what the person will conclude is, based on my data that I gathered, I'm 95% confident that the population mean that I'm interested in is somewhere between 33 and 41. And that's how a 95% margin of error leads to a 95% confidence interval for a population mean. And notice the steps I followed right here to get these two numbers, the two endpoints of the confidence interval. What I did to get this first one is I took the sample mean of 37 and subtracted 4 by 4 to go 4 out in this direction and get to 33. And what I did to get the other one, the upper endpoint, is I took the sample mean of 37 and added 4 to go 4 out in this direction and get to 41. So what you can see here is to get the 95% confidence interval for a population mean, what you actually do is you calculate the sample mean first, then you calculate the 95% margin of error, and then you take the sample mean and you add and subtract the 95% margin of error. And that's what gives you the two endpoints of the 95% confidence interval. So like I said, right here, it's just sample mean minus 95% margin of error, sample mean plus 95% margin of error, and this gives me a 95% confidence interval around my sample mean, which in this case came out to 37. And one way to think about it, one way to think about this 95% confidence interval is to think that I said that it's unlikely that the population mean is exactly 37, exactly the same as the population mean, but it's reasonable to think that the population mean is likely to be somewhere around the sample mean in the nearby area, because the sample mean and population mean tend to be close together if it's a random sample. So all we're really saying here is when we say we're 95% confident that the population mean is between 33 and 41, we're really just saying that we're not confident that the population mean is 37, but we're confident that it's somewhere in the nearby area of 37, more specifically, somewhere between 33 and 41. And we're not 100% sure, but we're just 95% confident that it's somewhere between 33 and 41 in the nearby area of the sample mean of 37.